So in this video, I'd like to go over the concept of work in physics. Imagine the following problem. So imagine that we have a level surface, we have an object, a block. Let's assume that to move this block, we apply a force F, and this causes the object to travel a distance from here to here. Let's call it D. Work is defined, I'll call it W, is force times distance. So for example, if the force happens to be 100 newtons and the distance traveled in the direction of the force, then the distance traveled from moving this object from point A to point B is D. So we have 100 newtons times 10 meters in SI units. And this is 1,000 Newton meters. And Newton meters is given in units called joules. So this is 1,000 joules. J for short, so standard unit of energy. Now, the direction of the force happens to be in line with the displacement. But in the case that the force is not in the same line as the displacement, so imagine that we have the following scenario again. We have an object, a box, on a level surface, and I push the box in this direction with 100 newtons. And it again travels a distance of 10 meters. But I'm actually pushing, so maybe the box is very big and I'm very, very small. This is mini-me pushing the box straight up. And so what is the work? Well, we have to find the component of the force that's projected along the line of the displacement. I'll call this angle theta between the force F and the displacement 10 by theta, and we can give it a number. Let's say it's 60 degrees. Actually, let's make it 45 degrees. 45 degrees. And so the projection of F onto the direction of the D would be given by a force, which is F cosine of theta. That's the force. That's parallel to the displacement. And then the displacement is D. And this is defined to be work. So in this case, it happens to be 100 newtons times the cosine of 45 degrees times the displacement of 10 meters. So this is 1,000 cosine of 45, if you remember, is 1 over square root of 2 times 10, and the answer is in joules. So this is the work done by me pushing on a force, pushing on a box in an angle of 45 degrees up. But it's always the component. So the force that I applied up is useless. That is no work. No work is done by me in pushing the object up. There was no displacement in the up direction. There was a displacement on the horizontal direction, but not vertical. So this is the definition of work. But if you kind of remember the definition of F, so we already have a definition of a dot product. So the definition of dot product, right, is defined to be, there's two definitions. If A dot B, we could say that that's the magnitude of A times magnitude of B cosine of theta, which just happens to be also equal to the x component. So if this is AXI, if the A vector is AXI plus AYJ plus AZK. Yeah, a little bit bigger. I plus AYJ plus AZK. So there's two definitions of dot product. One can prove the other, but we're not here to prove dot products. So this is the bx component in the I direction, the b component in the I direction, the y component in the j direction, and the z component in the k direction. And so we could also say that the dot product, right, is ax bx plus ay by plus az and bz. But let's just review to remind you what the dot product is. But if you take a look at f cosine d theta, right, we could also rewrite it in a different way, and that is, so let me erase this. Actually, let me write it in. So the work done is equal to the vector force times the displacement d. It's a dot product of f dot d, which in the dot product definition is actually just f d cosine theta, where I've used f to represent the magnitude of f, d to represent the magnitude of d vector, and cosine of theta is the angle between them. So it's a simpler definition, and let me give you an example to make sure we understand this idea. So we can extend this further, right, to an integral definition, and eventually a path integral. So the idea is that we can now define work to be the force times the dot product of the displacement. So let's do an example. A force and I'm going to assume standard units, so I won't put the units in any of the equations because it's too time consuming. I'll always assume the units are going to be in standard units, which in this case happens to be the kilogram, the meter, the second, and joules and newtons. So standard units in SI. So this unit is in units of newtons, N. And assume force of F causes the displacement of an object (2i plus 6i plus 4j). And you might be worried that the force and the displacement, right, are not in the same direction. And the idea is that they don't have to be. The force and the displacement do not have to be in the same direction. So for example, if you remember in the last example, I applied a force F, and the displacement of the object is parallel to the ground, but the force I applied was at an angle, at an inclined angle. So if you remember the last example, I was pushing against the wall, this block of wood, in an angle, but the force vector and the displacement vector do not have to be in the same direction. So in this case, we can use the definition of work to be, work is a scalar value, and it's equal to F dot D. In this case, it happens to be 3i plus 4j plus 6k dot with 2i plus 6, whoops, this is not an I, should be a j and a k, sorry, mistakes. So this is your j plus 4k. And definition of a dot product is 3 times 2 plus 4 times 6 plus 6 times 4. And so we'll get 6 plus 24 plus 24, which is equal to 54, and the answer is in joules. So 54 joules was the work done by this force to cause the object to displace by this displacement vector. So let's extend this further. So I'm going to actually draw a diagram. So imagine that we have a two-dimensional system. And let me get another marker. And and we have the position vector r of some particle. This particle, right, at time t, so I'm using r to represent the radial vector or the position vector. Object. And specifically I'm going to be r at t, meaning that at time t the position vector points to an object at time t, and at some time later, we'll call this at dt, so we'll get used to differentials, position of object at time t, and this is the position of object at t plus dt. So you get used to differentials instead of like delta. So the new position is over here. The displacement vector corresponding to this is dr. So dr, the differential dr vector, the vector that's drawn from the initial time to the final time, is the displacement vector. Here's your displacement vector. We're going to assume that there is a uniform force that's being applied across this. When the object travels from this position to this point, there's a force F. So using this idea, we can actually define the differential, the little small work that's done by a force F to cause a displacement of r vector. So just be careful, this d right now, right, is the differential, not the displacement vector as I did in the last example. And this is called the differential form of work. We can also do things like, for example, a definition of work. We can also define power, for example, if I had to. Power, the instantaneous power is the amount of work done in a small interval of time. So this is the average work done by the force to cause this object to travel from point at t to another point, t times t plus delta t, dt later. And that's equal to F dot dr vector over dt. And if you look carefully, right, this is actually just the force vector times the velocity vector. This is called the power. So this is the power, is just the velocity vector dotted with the force at any point in time. But actually, more importantly, let's not worry about power right now. Imagine that this particle, right, is now traveling in some path, convoluted path. And this is from at time ta to point tb. And so this path, right, I'm going to denote by gamma. So gamma is the path that the particle takes with this force, and this force is at various points in the path. So this force, right, is dependent on the path. So I'll write this as in terms of gamma, saying this is path dependent force. And we'll get another marker. So the idea is that the total work to go from time ta to tb is now given by an integral gamma, which starts from ta and finishes at tb of dw. But using the differential form of work, we can rewrite this in terms of gamma F dot dr, the differential. And so this is our standard definition of work that we'll be working with. So let me give you an example of this. So let me erase this. And this is Imagine that a particle travels with a position of r, so this is our radial position vector, that's why we're using r, is given by t I plus t squared j plus t cubed. And t is going from initial time 0 all the way to 10 seconds. So your position vector is in t meters, t squared meters, t cubed meters. I'll be using standard SI units. I just won't put the units in until I need to do some calculations. The position of t squared in a force field, sometimes referred to as a vector field. And this force field is given by xi plus 3yj plus z squared k. So at every point in space, this force field is not a function of time, but at every point in space, this field, right, has a certain direction. So if I looked at the point 0, there would be no force field, 0, 0, 0. If I looked at the point 1, 0, 0, that's along the x-axis, we expect a force field to be 1, 0, 0. So it happens to be in the same direction as that is to say that if I look at the point 1, 0, 0, and assuming that this is the x-axis, up is the y-axis, and z coming out of the board is the z-axis, then at this point in space, the force field is in this direction. But if I select a point that is 1, 1 over here, the force field, so if this is 1 and this is 1, so this is the point 1, 1, 1, and 0, then the force field is 3, 1. So it's got a component this and 3 times bigger, so it's not a very good But anyway, this is called a force field or a vector field. And ultimately the question is, find the work done from t is equal to 0 to t equals 10 seconds. So we're going to start off this integral right from definition, from our definition of work. And actually, let me write this down because I'm going to have to erase this board. I think I made it too big. So our force field is given by xi. So every point in space, we can define a force field. It doesn't change. It's a constant force field. But the direction of the force so this vector field, right, does not change in time. It's got a positional variance, but and we're told that the position vector is given by ti plus t squared j plus t cubed k. So it's our position vector. And we're told also that time is from 0 to 10, closed interval. So let me erase this and let's do our calculation. So the key idea is that our definition of work along this path that takes from t is equal to 0 to 10, which is equal to f dot dr. I'm now going to use the chain rule and say this path is equal to f dot dr. I'm going to divide by dt and multiply by dt, and this is our chain rule. And this chain rule, right, so what is dr dt? And if you think about it, dr dt is the velocity of the particle. the velocity vector. Let's calculate the velocity vector and let's do the calculation. Let me do it over here. So this is the derivative with respect to time of the position vector. In this case, it's ti plus t squared j plus t cubed k. I take a derivative. Notice the unit vectors, they don't change in time, so this will just be the derivative of t with respect to ti dt squared dt plus dt cubed with respect to dtk. And I forgot the j. So this is 1I plus 2tj plus 3t squared k. So let's continue with this integral. So what we have is a force. Now just to remind you, this is the position of the particle in the x-coordinates, the y-coordinates, and z-coordinates. So I'll just write this to make sure you understand. X is equal to t for the particle, y is equal to t squared, and z is equal to t cubed. And this is the parametric representation of the position. So here's your parametric representation of the, looks like a D, doesn't it? Parametric representation of your particle. So I'm going to convert this integral into an integration from t is equal to 0 to 10. Our force field, right, happens to be x3yz squared, but I can change that with, so actually let me put these steps in because I want to make sure that you're not mistakenly putting things in the wrong order. And because I do usually skip a lot of steps, but I think I better not in this case. So what is dr dt? That's the velocity vector, but I'll put it in the long way, which is basically, whoa. Actually, I'll put the short routine. This is over here. 1I plus 2t j plus 3t squared k dt. So this is the position vector. I'll now replace the x's, y's, and z's with our position of the particle. In this case, it happens to be the integral taken from 0 to 10 of ti plus 3t squared. Y is t squared, right? So this is t squared plus z squared. Z is t cubed, so this is squared. And this is j, and this is k, dotted with 1I plus 2tj plus 3t squared k dt. So this becomes t is equal to 0 to 10, t times 1, 3t squared times 2t plus, this is t to the 6, so I'll just write t to the 6 instead. T to the 6 times 3t squared dt. So we're left with an integral, again, of t is equal to 0 to 10 of t plus 6t cubed. Okay, so it's a 3t to the 8 dt. And we integrate, and the integral basically says that our integration limits, right, are from t is equal to 0 to 10. Our integral becomes 1/2 t plus 6 over 4 t to the 4th plus 3 over 9 t to the 9 taken from t is equal to 0 to 10 in 10 seconds. So this is now just 1/2 times 10 plus 3 over 2 times 10 to the 4th plus 1/3 times 10 to the 9. And the whole answer is in joules. So this is the work done by a particle that has a position vector of t squared t cubed in a vector field xi 3y j z squared k when the object travels from time t equals 0 to 10. So this is an example of calculating a path integral. So this is called a path integral. Now what's really interesting is we defined work to be F dot dr, and from this definition we can rearrange things and actually relate it to something called kinetic energy. So let me erase everything and let's go back to the definition of work. So our definition of work is the path gamma of a particle that experiences a force and a differential displacement of its position with dr. Now what I'm going to do is, in classical mechanics, right, I know that we can, well, multiply by dt and divide and multiply by dt, which is our chain rule. In the next step, I know force, right, is the change in the mass times velocity, or change in momentum per unit time. There's gamma. And dr dt is the velocity vector dt. Now we know that in classical physics, only in classical physics, we expect m to be not a function of time. And again, this is kind of really problematic because so relativity considers mass, right, even mass, to be something does not change. But the effective mass, right, or the effective momentum of an object, right, does change when the velocity approaches proportionate to the speed of light. But in classical mechanics, we just have to assume that this mass or this momentum, right, does not really change in time, and mass can be factored out. This is only true in classical physics. And classical physics, right, we can assume classically this is true up to even a couple of percent the speed of light. So even 1% the speed of light is 1 over 100 times 3 times 10 to the 8 meters per second. So this is 3 times 10 to the 6 meters per second. 3 million meters per second. That's very, very fast. So we don't even have to worry about worrying classical physics. So let's assume it's classical physics. So the m comes out. I'll rearrange this and put the v vector dot, since a dot b is the same thing as b dot a, I'm using the chain rule. We cross out dv, and this is our gamma path, right? Here's our mass. And v, I'll now expand this and say that the vx component, I plus vyj plus vzk, is the vx component, and the differential is given by dvx I plus dvyj plus dvzk. I'm doing it really long. We actually would skip all these steps, but if this is the first time you've seen this, right, I'm trying to simplify it as much as possible so you don't kill yourself in trying to understand this concept. So the dot product is now the integral of vx dvx plus vy dvy plus vz dvz. And that's equal to exactly the same as the path m gamma of dvx squared over 2 plus dvy squared over 2 plus differential of vz squared over 2. So this is actually, the whole thing is being integrated. And we can solve this and say this is really the mass times the difference in the endpoints of vx squared plus vy squared plus vz squared all over 2 endpoints. And that's equal to, well, if you think about it, right, this is really 1/2 m times the velocity squared taken at the endpoints. So this is the change in the kinetic energy from final to initial. So what you're saying is that if we have some force being applied on an object across some path gamma, then that is equal to the change in the kinetic energy, or if you want the kinetic energy, if 1/2 mv squared minus 1/2 mv initial squared. So the initial velocity is the initial velocity of the particle before the across the path, and the final velocity at the end of the path. And this is another definition that we really need to know. So in the last example, whatever number we get for the work, that's equal to the change in the kinetic energy of the system.